All right, today we're going to continue in our calc lessons. We're going to be doing the second part of 2.3, 2.3b. And the next thing we're going to learn about in 2.3b are derivatives of other trig functions. So we talked about the derivative of sine and the derivative of cosine, but what about the derivatives of the other main 6 trigonometric functions? So theorem 2.9 in the text has the derivatives of these other trig functions. The derivative of tangent of x is secant squared x. The derivative of cotangent of x is the opposite of cosecant squared x. The derivative of secant x is secant x times tangent of x. And the derivative of cosecant of x is the opposite of cosecant of x times cotangent of x. I know, a little more complicated than the derivatives of sine and cosine, right? Well, let's just practice it. And in example 12, this wants us to find the first derivative, and we're going to find the derivative of tangent x secant x. And notice that we're finding the derivative of two functions involving x that are being multiplied by each other. And so we are going to, in addition to using these new rules for these derivatives, we're also going to be using the product rule. So we have dy dx equals, and then with the product rule, remember we're going to take the first times the derivative of the second plus the second times the derivative of the first. Okay, and I know we're probably used to that at this point, but because these trig derivatives are new, I'll write it out for this one, okay? So again, we're going to have tangent of x. And now let's find the derivative of secant x. It says the derivative of secant x is secant x tangent x plus, now we have secant x, and now we're going to take the derivative of tangent x, which is secant squared x. And now we can simplify each of those terms. So if I multiply here, I see that I get tangent squared x secant x, and then here I have secant cubed x. So, I mean, that's fine. I mean, you could think about if you could cancel anything, you can't from tangent times secant, right? So this is a fine way for you to write your derivative. Tangent squared x secant x plus secant cubed x. If you factor the secant out instead, like if you put secant x times tangent squared x plus secant squared x, that's fine. So that's fine too. So a couple different ways that you can write it. Just make sure that it's equivalent to the answer that we should get. In letter B, I have y equals x times the secant of x. Again, I have a function involving x multiplied by another function involving x. So once again, I'm going to be using our product rule. So to find my derivative, I'm going to take the first times the derivative of the second plus the second times the derivative of the first. So the derivative of secant x, again, we said is going to be secant x tangent x. And now I take the derivative of x, which is just 1. And so I could call this x times secant x tangent x, and then plus secant x as my y prime. I can't combine any of those like terms. Again, if you really wanted to, you could factor out a secant x. And you could have x times tangent of x plus 1 as a factor. That's fine. Okay, so that works. Letter C, I have k of theta equals 2 sine theta. Oh my goodness, we don't know what to do. We haven't learned derivative rules when we have something other than just like x or theta or t as our input. So, because that's going to be a story for another day. So if we have the sine of 2 theta, we're going to have to revise this, okay? So we must revise since we can't do 2 theta yet as an input, okay? So how in the heck could we rewrite sine of 2 theta? That's right, the double angle formulas. Let's rewrite this as 2 times the sine of theta times the cosine of theta. Well, that's nice. Now I have 2 functions being multiplied by each other involving our input variable theta. And so then I can indeed use the product rule. So I could say that k prime of theta is going to be 2 times, like pull out that 2 as the constant multiplier, and then use my product rule. So I would have sine theta. Are you guys ready to kind of skip the next step? Okay. Times the derivative of cosine theta. Remember, the derivative of cosine theta is going to be the opposite of sine of theta plus my cosine theta times the derivative of sine theta. And the derivative of sine theta is cosine theta. Okay. If you want to write out the derivative part first, that's fine. I'm just trying to save a little bit of time here. Kiddos, okay? So let's see what this would be. This would be the opposite of sine square theta plus cosine square theta. And cosine square theta minus sine square theta is a double angle formula, right? We don't have to pull out a negative, it's just that the terms are flip-flopped. So we can see that this is going to be 2 times the cosine of 2 theta. So again, from here to here, again, we're going to use another double angle. And that looks so much nicer. Doesn't it look better when we use the double angle formula? And that would be my k prime of theta, is 2 cosine 2 theta. Cool. How about letter D? 9 times the cosecant of x plus x times cotangent of x is what our value of f of x is here. And I see that I have 9 times the cosecant of x. I don't need to use the product rule here because that's just a constant multiplier. But I have x times the cotangent of x, and I'll have to use the product rule for that part, all right? So if I take my f prime of x, I want to take the derivative of 9 times the cosecant of x, okay? And I look, and the derivative of the cosecant of x is negative cosecant x times the cotangent of x. So I'm going to take 9 and then times the opposite of cosecant x, cotangent x, and that would be my derivative of 9 times the cosecant of x. Okay. Now I have plus, and now I'm going to use the product rule. I'm going to take x times the derivative of cotangent x. The derivative of cotangent x was the opposite of cosecant squared x. So times the opposite of cosecant squared x. And then when I use the product rule, I'm going to then add the cotangent of x times the derivative of x, which is just 1. So now let's clean this up a little bit. I would just rewrite this as the opposite of 9 cosecant x cotangent x minus x times cosecant squared x plus cotangent x. And we can't really combine any like terms here, right? So that's going to be about it. Make sure I see the prime. I know mine kind of blend in. Sorry about that. You also could factor out a negative here if you wanted. Like you could say the opposite of 9 cosecant x cotangent x plus x cosecant squared x minus cotangent x. Again, just lots of different ways that you could write that, okay? All right, so that is using our trig function derivatives with our new trig function derivatives with our product rule. In example 13, this wants us to calculate the derivative by hand, and then I'm going to show you how you can use your graphing calculator to help you out as well. And we're going to do that at the point 1, -1, or just kidding, 1, 1. So our function is defined as tangent x cotangent x. And so let's practice our derivatives by using the product rule here and see what we get. All right. Again, I know that there are reciprocal identities going on, which would be much faster, but I'm just trying to practice with you, okay? So this is going to be equal to the tangent of x. Now we want the derivative of the cotangent of x. So that's negative cosecant squared x. And then plus cotangent x times the derivative of tangent x, which is secant squared x. Okay. So one thing we could maybe do is put everything in terms of sine and cosine and see if we could cancel. So if I did tangent x, that's like sine of x. Oh, this is f prime of x. My bad. That was very bad for me not to label that. I'm sorry. So that would be sine of x over cosine of x. And then this would be -1 over sine squared of x. This would be cosine x over sine of x. And this would be 1 over cosine squared x. And so let's see what we've got here. These signs, one of the signs cancel. So this 1 over cosine of x is really going to be like secant x. And this -1 over sine of x is really going to be like negative cosecant x. One of these cosines canceled, so 1 over sine of x is going to be like, just kidding, cosecant x. Wow. And then 1 over this cotangent x is going to be secant x. Do you guys see that I really have negative secant x, cosecant x, plus cosecant x, secant x? These are going to cancel out, and that gives us 0. Okay. So our slope should be 0. Now, how could we do this on the graphing calculator? Sorry, I had to grab mine. Well, you could put that in, and you can do this for any function as well, not on your quizzes though. Okay, so we're going to take, what was the function? Oh, tangent of x times the cotangent of x. So that's going to be 1 over tangent of x. Oops. Okay, and when I graph, I always zoom trig it. So zoom 7. And that makes sense, doesn't it? Because those are reciprocal functions, that's going to be 1. So then, of course, the slope is going to be 0. But let me show you how to do this on the calculator. You can calculate the value at a derivative by doing second trace to get to the calc menu. So if you go to second trace, and then you hit number 6. Oh, so I don't know if you need that as a little reminder. Yeah, this is going to be second trace to get to this menu. And then you can go down to number 6, which is dy dx. And then this is supposed to say, this didn't copy well on mine. I hope it did better on yours. We want to put x equals 1 there. And so all we have to do is press 1 to have the calculator evaluate at x equals 1. So if I have this here, and again, notice it says calculate derivative at point, then I hit 1, and then I hit enter. Notice it gives me the value. It says that dy dx is going to be 0. So at the point 1, 1, it gives us the value of the derivative. So that's kind of cool, right? Good little thing to know. Okay. So now we're going to go on to higher order derivatives. All right, so we're going to be looking at these higher order derivatives. Remember that we obtained a velocity function by differentiating a position function. And I did mention that we can then obtain an acceleration function by differentiating a velocity function, okay? Or what we could do is obtain an acceleration function by differentiating a position function twice. So that's a way that we can think about that, all right? So this is a very important concept for us to think about, that when we have s of t, that's our position function. When we have v of t, that's the derivative of the position function, that's the velocity. And a of t, our acceleration, is the derivative of the velocity, which is the second derivative of the position function, okay? So again, a of t is the second derivative of s of t. And notice I wrote over it, but it's denoted by s double prime of t. So that's an example of a higher order derivative. So just kind of to review, since we're talking about this, units for velocity. Velocity is distance over time. So the units for velocity that we'll see are things like meters per second or feet per second. But acceleration is distance over time, the velocity, divided by time. So that means that we end up with meters per second squared or feet per second squared. And technically, we're supposed to say meters per second per second. So me if I keep saying per second squared, but we are supposed to say meters per second per second. So get on me if I don't say it correctly. So we're going to be seeing this notation a lot more now that we're going to be able to find the acceleration, since we're going to be doing these second derivatives. Again, higher order derivatives are obtained by repeatedly differentiating a function, y equals f of x, provided that the derivative exists. So again, if f prime is differentiable, then the second derivative is denoted by f prime of x or y prime, okay? The third derivative is the derivative of the second derivative. So the third derivative is like y triple prime. The fourth derivative, we usually looks like this. It's not y to the fourth power. But so sometimes instead of writing it like that, it's safer to write it like this, d4y dx4, and that implies that we're finding the fourth derivative, okay? I think this is interesting. It can be said that f of x is the 0th derivative. I like that. All right, so let's try to find some higher order derivatives, folks. In example 14, let's find f double prime of x, so the second derivative of f of x, given that f of x is the secant of x. So let's try to find f prime of x, all right? So if I look at what f prime of x is, I want to take the derivative of secant, and remember the derivative of secant is secant x tangent x. So now I want to take the second derivative, which means I want to take the derivative of secant x tangent x. Well, guess what? We're going to have to use our friend, the product rule, because we have two functions involving that input variable, secant x and tangent x. So to use the product rule, I know I'm going to take the secant of x, and now I want the derivative of tangent of x, so that's secant squared x, plus, now I take the tangent of x, and I multiply it by the derivative of secant of x. And again, the derivative of secant of x is secant x tangent x. And then I can just simplify that a little bit. So that gives me secant cubed x plus, I don't know, would you say secant x tangent squared x or tangent squared x secant x? Doesn't matter, right? And we can't combine those, so that would be my f double prime of x. Of course, you could factor out a secant if you wanted and rewrite it as secant x, secant squared x plus tangent squared x. That's fine, okay? So a lot of different ways that you could write it. Example 15 wants us to find the third derivative at x equals -1. For f of x equals 3x to the fifth minus 2x squared plus 7x to the -2. Well, the first thing we're going to have to do is find the first derivative. Okay, so the first derivative, f prime of x, well, actually, let me call this df dx to be consistent with their notation. Okay, so df dx is going to be, and we've done this enough, this is going to be 15x to the fourth minus 4x plus, negative, so minus 14x to the -3. Okay. Now what we want to do is to take the derivative of this. Okay. And so if we take the derivative of that, that gives me d squared f dx squared. And so let's take the derivative of this. That would give me 60x cubed minus 4, and so now plus 42x to the -4. Well, now guess what? Now we want to take the derivative of this. And so to find the third derivative, I'm going to take the derivative of the second derivative. So that would give me 180x squared. The constant would turn into 0. And so then minus, what is that, 168x to the -5th. Okay, so this tells me how I can evaluate my third derivative. Okay, and now we want to evaluate this third derivative at x equals -1. Okay, so now we're going to evaluate this third derivative at x equals -1. So we can just put -1 in for x. And this one isn't that bad. This is really going to be 180 times +1 minus 168 over -1. If I take -1 to the -5th, that'll just be -1, whatever. So essentially that's going to be 180 plus 168, which is going to be 348. So that tells me that f triple prime of -1 is going to be 348. Okay, so again, those notations are consistent throughout. Okay, like those notations mean the same thing. All right. So find the acceleration due to gravity. Let's do a story problem that deals with this. So you guys, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. So what that means is that a feather and a hammer would fall at the same rate on the moon. The position function of these objects is given by s of t equals -0.81 t squared plus 2, where s of t is going to be the height in meters and t is going to be the time in seconds. It says, what is the ratio of Earth's gravitational force to the moon's? Well, you guys, when it says Earth's gravitational force, that's going to be like our acceleration. Okay. And just a little FYI, the acceleration due to gravity on Earth, we've discussed this before, in meters per second is -9.8 meters per second per second. Look, I said it right. I'm growing up, guys. Okay. So if we want the ratio of the Earth's gravitational force to the moon's, we know the Earth's gravitational force, but we need to find the moon's. And so what we can do is use the position function that's given here to help us out. Okay, so the first thing that we can do is take the velocity. Okay, well, that's our thing. So we're going to find the acceleration on the moon. Okay, so the velocity is going to be s prime of t. So if I took s prime of t, that'd be 2 times the coefficient, negative 0.81. So that gives me negative 1.62 t, and that velocity would be in meters per second. And so then the acceleration is going to be s double prime of t. So I would take the derivative of this, and that's nice. It's just going to be negative 1.62. And so meters per second. Okay. So now it does ask us to then find the ratio. And it says of the Earth's gravitational force to the moon's. So we said that Earth's is about negative 9.8 meters per second, and the moon's is about negative 1.62 meters per second. So our units would cancel. So then we would just take negative 9.8 divided by, negative 1.62. Oh, and that gives me about 6.049. So what that means that it's about 6.049 to 1 if we're doing a ratio. So that means that Earth's gravitational force is about 6 times as strong. Okay, but that would be our ratio, about 6.049 to 1. And again, that means it's about 6 times as strong, the Earth's gravitational force. So I heard that means that you'd weigh less on the moon. I need to go there. Okay. So example 17 says an astronaut standing on the moon throws a rock into space. The height of the rock is s of t equals negative 27 over 10 t squared plus 27t plus s, where s is measured in feet and t is measured in seconds. So let's find expressions for the velocity and the acceleration of the rock. So the first thing is that we know that our velocity is going to be s prime of t, right? So let's find s prime of t. So I can take 2 times negative 27 over 10. Well, I'll just do this. So negative 27 over 10 times 2t, and then plus 27, and then we have plus 0. So essentially, s prime of t, we can cancel this here, is going to be negative 27/5 t plus 27. And remember that this really is also the velocity. Okay. So that's our expression for the velocity. And so now we can find the acceleration by taking the derivative. Okay. Remember, the acceleration is s double prime of t. And so then s double prime of t is going to be the derivative of the velocity, the derivative of the first derivative. So we would just take negative 27 over 5 and then plus 0. And so then that means that our, just a of t which is the same as s double prime of t, would be negative 27 over 5. Let's put that as a decimal. So that's going to be about negative 5.4, and then feet per second. Okay, and I guess here I should put a unit on this too, shouldn't I? This is going to be feet per second. So the velocity is negative 27/5 t plus 27 feet per second, and the acceleration, notice, would always be negative 5.4 feet per second. Letter B says, find the time when the rock is at its highest point by finding the time when the velocity is 0. And then what is the height at that time? So the first thing that we're going to have to do is to find when the velocity is 0. So let's find out when v of t equals 0. We have an expression for v of t, so let's set that equal to 0. And we can solve. So I'm going to move the 27/5 t, and then I can multiply by 5/27, and I see that t is going to be 5. So I see that the velocity is 0 at 5 seconds. Okay. So again, when you think about when the rock is thrown up, then do you see how the velocity is going to be at 0 at that point? It was increasing and then decreasing at that point. Okay. You'll learn more about that later. Okay. And then the next thing that we need to do is find the height at that time. So we want to find the position at t equals 5. So which function gives us the position? S of t. So make sure we use our position function, and we're going to find s of 5. So that was the negative 27/10 t squared plus 27t plus 6. And so you can put that in your calculator if you want. Hopefully you trust me. And we end up getting about we get 73.5 feet. So that would be the highest point. Okay. And again, guess what your vertex is, guys? Yep. Okay. So again, that's going to be the vertex of that particular original function. So one more question: how does the acceleration of the rock compare with the acceleration due to gravity on Earth? So again, the acceleration of the rock is going to be s double prime of t. Remember, that's our acceleration. And the acceleration due to gravity on the Earth is going to be that g. And remember, if we're dealing with feet per second, that is the negative 32 feet per second. Okay, so that's our acceleration on the Earth due to gravity. So we know g, now we just have to find s prime of t. So let's think about our acceleration. We know that from up here, right? What we did is we found that s prime of t, which is the moon, s double prime of t, was going to be negative 5.4. I'll write the units this time, feet per second. And the Earth's gravity is negative 32 feet per second. Oops, sorry about that. The Earth's gravity is negative 32 feet per second. And we can see that our units cancel out. And so let's divide that out. Negative 5.4 divided by negative 32. All right. So that's about 0.169 to 1. Okay. Or 0.169. You could write it a couple different ways. But that's how the acceleration of the rock compares with the acceleration due to gravity on the Earth. So we can use the second derivative to find the acceleration and then compare it to the knowns that we have on Earth. And that is all I have for you, right? Yes, on section 2.3. So let's get ready for section 2.4. That's even more exciting. All right, have a great day.